You are all welcome to our fifth presentation in atomic structure and bonding. Earlier on, we discussed the nature of overlap and the kind of bonds that are formed, in which we are able to talk about formation of sigma and formation of pi bonds under covalent bonds. Today, we are looking at the concept of hybridization. The concept of hybridization can be easily understood if we use the following example, that hybridization can be likened to mixing up. When you mix up such that we have an outcome that is the same or tends towards being almost the same nature. For example, an example we can give here is, say for example, if you decided to mix s orbitals with p orbitals such that the outcome gives us orbitals that have properties that tend to be half s half p kind of orbitals, then we say hybridization has taken place. Let's go to the concept of hybridization. The process of intermixing the orbitals of slightly different energies so that we have redistributed energy. If we have redistributed energies amongst them, resulting in the formation of a new set of orbitals of equivalent energies and shape, that is what is referred to as hybridization. The main features of hybridization are: 1. The number of hybrid orbitals is equal to the number of orbitals that were intermixed or hybridized. 2. The hybridized orbitals are always equivalent in energy and shape. 3. Hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. 4. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs, and thus they actually come to a more stable arrangement. Type of hybridization indicates the geometry of the molecule that will result. Important conditions of hybridization. The orbitals present in the valence shell of the atom are hybridized. 2. The orbitals undergoing hybridization should have almost equal energy. 3. Promotion of electrons is not an essential condition prior to hybridization. And number 4, half-filled orbitals and filled orbitals of valence shell take part in hybridization. Types of hybridization. sp hybridization. From the name itself, sp, implications are: this implies that there is one s and one p orbital that intermix or hybridize to give us two sp hybridized orbitals. They appear like the diagram, like the drawing, like the caption that appears on that particular slide. It involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. Each sp hybrid orbitals has 50% s character and 50% p character. A molecule which the central atom is sp hybridized and linked directly to two other central atoms, possesses linear geometry. It provides more effective overlapping, resulting in the formation of stronger bonds. The bond angle is 180. The second type of hybridization is sp2. This involves 1s and 2p orbitals mixing in order to form 3 equivalent sp2 hybridized orbitals, like the drawing or caption that appears on that slide. The orbitals will appear like that one. For example, in bromine chloride molecule, the ground state electronic configuration of the central boron. In a boron chloride molecule, the ground state electronic configuration of the central boron atom is 1s2, 2s2, 2p1. In this particular boron atom, the implications are that we have 2p orbitals that are actually vacant. They have no electron in them. So we have vacant p orbitals at that level, meaning that boron can actually show that it can form different bonds, but we can also have the mixing of the 2s and the 2p orbitals to give us several orbitals. Here it will be easy to do that. So on the other hand, like we said, we have two vacant p orbitals. These ones can have electrons go into them so that we form sp2. In the excited state, one of the 2s electrons is promoted to the vacant 2p orbital. As a result, boron has 3 unpaired electrons. These 3 orbitals, 1 2s and 2 2p orbitals, hybridize to form 3 sp2 hybrid orbitals. The 3 hybrid orbitals so formed are oriented in a trigonoplanar arrangement and overlap with the 2p orbitals of chlorine in boron-chlorine bonds. Therefore, in boron chloride, the geometry is trigonoplanar with the boron-chlorine bond angle of 120 degrees. sp3 hybridization. This one normally takes place when one s orbital overlaps or mixes. It mixes completely with 3 p orbitals of the same valence shell. The example we can give here is when we have carbon atom. In carbon atom, like we said before, we have 2s orbital which has 2 electrons, and we have 3 2p orbitals, but in which we have 2 p orbitals having single electrons occupying them and 1 p orbital which is vacant. That is when we have carbon in its ground state. When energy is provided to carbon in its excited state, an electron from the s orbital is promoted to the p vacant orbital. Therefore, we will have 1 electron in the 2s orbital, and then we will have 1 electron in each of the 3 p orbitals of the valence shell. If these 4 orbitals mix up, they form 4 sp3 hybrid orbitals of equivalent energies and shape. The 4 sp3 hybrid orbitals formed are directed towards the 4 corners of a tetrahedron. Therefore, carbon in methane tends to form a tetrahedron. The angle between the sp3 hybrid orbitals is 109.5 degrees. The geometries of molecules from the examples of sp2 and sp3 hybridization, we have examples that have been given here of what kind of geometry are we going to have of the molecule that is going to be formed. It depends on the geometry of the orbitals that are going to be used for bonding. In case we talk about sp, we said that the bond angle will be 180, and therefore the kind of structure that will be formed will be linear. It is a linear structure. An example that has been given here is carbon dioxide. The central atom being carbon and the other two atoms on either side being oxygen atoms. Then the second one is when we talked about sp2 hybridization. I know we gave an example of boron and we talked of boron chloride, but we can see that here on our slide we have boron fluoride. When boron reacts with fluorine, we have a trigonoplanar kind of molecule formed with a maximum bond angle of 120. But this is the case when we have bonds between boron and fluorine. But earlier on in our studies, we had also mentioned that the same thing can happen when we have a lone pair of electrons. It behaves as a pair of electrons in a bond. An example that has been given here is nitrogen dioxide, in which we have a lone pair of electrons repelling the pair of electrons in the nitrogen-oxygen bonds, such that we have a similar kind of appearance of the molecule, that the bond angle between nitrogen-oxygen bonds is going to be similar to that one in boron fluoride. But because this side of the lone pair we don't have any attachment, this one forms what we refer to as a bent structure. The same thing happens with water. Oxygen-hydrogen bonds exactly form the kind of bond that we see here in nitrogen dioxide, and actually the lone pair on oxygen also residing on one side of the molecule forms a bent structure in water. In the trigonal planar and bent structure, we can see that we have involvement of three pairs of electrons. A pair in trigonoplanar, pairs of electrons are from the bonds, whereas in the bent structure we have a pair of electrons which is not from a bond formed but from a lone pair, and the other two pairs are from the bonds formed. In the other arrangement, that is when we have tetrahedral structure, we have, like we have said before, the bond angle is 109.5 degrees, and we gave the example of methane, in which we have the central carbon as carbon atom, and to the different points or to the different corners of the tetrahedron, we have hydrogen atoms appearing there, and the bonds formed between hydrogen and carbon in the center tend to be at an angle of 109. Then we have in ammonia, in which we have the central atom as nitrogen, and we have three hydrogen atoms bonding to nitrogen and a lone pair of electrons actually on one side. If on the side of the lone pair we had an attachment of an atom, then we would go back to the tetrahedral shape. But because that side there is no attachment to any atom, the only atoms will appear at the corners where we have hydrogen, hydrogen, and hydrogen attached to nitrogen in the central region. This one becomes trigonopyramidal. The trigonopyramidal is therefore the shape of the ammonia gas molecule. Thank you very much for your attention. We'll be back for our 6th presentation.